We have another operational experiences story. This time Rob is going to be talking about the latest upgrade to the Janet academic backbone. While we're waiting for the slides to come up, just a couple of quick admin points. Although we're not breaking for coffee this morning, there is fresh coffee available if you want to quietly duck out the room.
So take your time, please.
That's certainly an option. And also, speakers, just double check where you are in the running order, because I made some changes to it last night. And make sure that you get wired up with the microphone through the AV control room well in advance of speaking. Okay, Rob.
Thanks. Good morning. Right, as Keith said, I'm Rob Evans. I work for Janet, and my boss is called John, so I do indeed work for Janet and John. And I'm going to talk about what we've been doing recently to upgrade the network backbone. So for those that don't know, Janet is the UK's national research and education network. We connect all the universities, further education colleges, research establishments to the internet, to each other, and to other research and education networks around the world. The marketing figure is we've got a potential user base of 18 million. But Janet is built up in two bits, really. We have a backbone and we have regional networks. Sites connect to regional networks, and then regional networks connect to the backbone through two diverse fiber routes. There's about 20 regional networks around the country. We then have 2 points of presence in London Docklands, where the rest of the UK internet seems to be based, which has most of the external connections. So that's the stuff for transit and peering. And what I'm going to talk about today is just the backbone. So the fiber network for the backbone looks pretty much like this, the simple view, from Glasgow up in the north down to Warrington, Leeds, Reading, London, Bristol, and then Docklands. Geographically, it looks a very crude map, looks a bit like that. And on top of that, we have the circuits. So these were all 10 gig circuits, which was, most of the traffic comes from the two Docklands sites into, most of the traffic on Janet is really from external connections. So it comes into the Docklands sites, then out to the rest of the network. We did end up with also a mesh of circuits from Docklands straight to Warrington and Leeds as well, but I'll cover that later. Right, so on top of that fiber, we then have an optical infrastructure. This is Sienna Core Stream Regional Systems and Sienna 4200s. The optical equipment and the fiber is dedicated to us, but not managed directly by us. Verizon Business run the network, but we have read-only access to the management systems. So they do all the day-to-day management. They build circuits. They trace up faults, but we can see at quite a low level what's going on. Most of the circuits are SDH rather than 10 gig E. When we were building SuperJanet 5, which is the name of the current network, back in 2006, we still preferred all the diagnostics, error counters, alarms that you can get for SDH, which still isn't there really for 10 gig E. And then on top of that, we have the IP layer. It's Juniper T-Series routers in most of the backbone POPs, quite a few Ciscos too, everything from 7200s up to GSRs. And in contrast to the optical layer, which is managed by Verizon, the IP layer is managed in-house by myself and my colleagues. Right, so that's what the network was. Why do we need to increase it? Well, it's the usual up and to the right graph that everyone has to show at some point. These are the peak daily 5-minute values from 2005 through to the start of this year of the blue line, which is traffic coming into Janet, and the orange line, which is traffic going out of Janet to the rest of the world. As you can see, the days of Janet being a net traffic exporter are long gone. So to get all this traffic in, and you can see it's peaking at about 35 gigasecond at the start of this year, we added the extra links in from, using the optical layer, we added the links in from Docklands straight to Leeds and Warrington, but we needed to go beyond that. Now, what were the options of that? Well, we could add yet more 10 gig circuits, or we could try and use faster circuits. We chose to try the faster circuits for a couple of reasons. First of all, on the client side, so the router side, we're simple people. We like simple networks. We find them more reliable. We prefer having one link to multiple links because it's easier to manage. And some of the users on Janet are scientists that deal with large point-to-point data flows. If they're happening regularly, we can separate them out at the optical layer. But a lot of them are just kind of bursts here and there. And if we had a bunch of 10 gig circuits, there's a very real risk that some of these flows could overload one link in a bundle because it's not going to be spread evenly because it's all one IP to another IP. So that's on the client side. On the line side, the optical side, there's quite a lot of demand on Janet for research use of wavelengths as well. So we don't want to use more wavelengths than we need to. And to a lesser extent, as a R&E network, we're a little bit expected to be on the bleeding edge or the leading edge, whichever way you want to put it, within reasonable constraints of cost and while still keeping a stable network. And of course, lighting extra wavelengths is expensive as well. So, what were the options? What kit did we have to drive these? Well, given we had the Sienna equipment already, the first look was at the Sienna cards. They're made by a company called Stratolight. There was a first generation card available when we were started looking at this sort of 2007. Now, I'm going to talk a bit more about PMD and what that means a bit later on. But the key figures here are that the PMD tolerance, the polarization mode dispersion tolerance, was a group delay of 2.1 picoseconds for the first generation card, which used very simple dual binary encoding. Sienna had already announced a second generation card was on the way. And that used that used DPSK encoding, which had a much higher, a slightly higher tolerance, which could be raised with compensation. Doing all this, Sienna were making quite clear that their efforts were focused on 100 gig rather than 40 gigs. So that's why they were buying in the cards from elsewhere. So those figures, 2.1 and 2.5, how do they map on to the fiber we have? Well, for most of the fiber, quite good. Glasgow isn't on here. There wasn't enough traffic to warrant the upgrade when we were looking at this. And we've got no idea what the figures for those fibers are at the moment yet, but given the number of fiber cuts around there from all the pikey steel in the fiber, I imagine they're probably pretty poor. So most of the fiber, so from Docklands into London and Reading, that's all green, it's all below 2.1 or picoseconds, and similarly, the cross-country links from Warrington to Leeds and from Bristol to Reading, they're fine. But the two links from London up to Leeds and from Reading up to Warrington, they're slightly outside 2.1 picoseconds. They're outside 2.5, they're even outside 8 picoseconds. So we need to have a different solution for that. So, before rolling this out across the network, we had to try and figure out if it was going to work at all. So we had, before the rollout, we had a trial. The trial was from Telehouse to London. So if you look at this, go back to the fiber map here. This one link here, which was from Telehouse to London. It's about 25 kilometers of fiber, and Verizon had a spare fiber in the same bundle as the router we were using for everything else. That was well within the spec of the first generation cards which were then available. And we were able to borrow some interfaces from Juniper. And when I say borrow, I mean promise to buy. The logistics for this were a bit more complicated than the technology, really. Getting Sienna and Verizon and Juniper and our support partner with Juniper, Alcatel-Lucent, to do everything at the same time was far more complex than actually just plugging the cards in, at which point it pretty much just worked. So we installed it, it worked. A month later, we took it off the main fiber and put the wavelength across the production link, and it stayed working. So I think we classed the trial as a success, and we wanted to then move on to the rollout. So if you remember the figures, we decided to split the rollout into 2 phases. The first phase was the low-hanging fruit, the green links from Docklands into London and Reading. Links that could be handled by the Sienna kit, but still essential because they're some of the busiest bits of the network. Then for the second phase, we'd do the long-haul links, the links going north, for which we needed to find a different solution. And so geographically it looked like that. So we have the red links are the phase 1 links, and the green links are the phase 2 links. So phase 1 kicked off in June 2008. That was going to use the second generation Sienna cards. We decided to wait for those because they'd have longer life. They had a slightly better tolerance for the fiber. So as fiber ages, so it gets worse. Plus also there's cuts and splices as it gets fixed and moved and that sort of thing. And that didn't really add much of a delay. It did, however, require software upgrades to the 200-odd existing Sienna shells in the network to work with the new management software. And that did take a while. Verizon, of course, handled all of this, but it still, it ended up being September before the phase 1 stuff was ready. I'm going to talk about the IP side of this later, just to keep you interested. So the second phase then, as I said, was outside spec, way outside spec for the Sienna cards, even with the external dispersion compensation. So we had to find another solution for that, and the solution that Verizon came up with was to use Nortel. Now the Nortel optical kit uses polarization multiplexing differential quadrature phase shift keying, which I'll assume you all know what that means, which will then be carried as an aiding wavelength, so again, just carried purely optically on the Sienna stuff in the middle. I think there might be one question at the back, so I'll quickly explain what the Polmux DQ-PSK is and how it works for us. The way a signal is encoded onto the wavelength, normally 10 gig signals are pretty basically encoded. It's fairly close to just switching the laser on and off. That is, however, quite bandwidth hungry. So when you want to encode higher speed signals, you start using things like phase shift keying. And phase shift keying is what it sounds like in a way. It's you just shift the phase of a continuous carrier to indicate whether you're transmitting a 1 or a 0. Now, if you are shifting it by 180 degrees, then you can then overlay another carrier that's shifted by just 90 degrees, and then shift that another 180 degrees to indicate a second data stream. So you get your data stream of 10 gigaseconds or 40 gigaseconds coming down, and you split it up into 2 5 gig or 20 gig signals. So you have an in phase and a quadrature phase, add them together, and you get your quadrature phase shift key signal there. And that means basically, it's going back to the modem days, you can carry more data on a given frequency. So with this, you get 2 bits per symbol, and when you get the spectrum spread into account, that means you get about 1 bit per second per hertz. So that means on a kind of 50 gigahertz ITU grid, you can get about 50 gigaseconds using this. The Nortel stuff was the first to do polarization multiplexing on this. So you have 2 signals like that, the 2 DQ-PSK signals, and you just send one with horizontal polarization, one with vertical polarization down that fiber at the same time, and that doubles your bandwidth. So now you're getting about 2 bits per second per hertz, and so within a 50 gigahertz ITU optical grid channel, you can transmit 100 gigaseconds. Using fancy error correction, forward error correction, you can get 112 gigaseconds, which is the frequency that's going to be standardized for carrying 100 gig signals. And you get that within a single 50 gigahertz optical grid. So, to do this, we needed to buy the Nortel kit, which was going to be expensive. Fortunately, it wasn't our problem. When we'd done the Supergiant 5 contract, we'd said to Verizon that in 2008, you will supply us with 40 gig on the links that we mentioned there. And they signed up and said yes. So they thought it would just be a case of buying a few more shells for the Siennas. What they hadn't realized that they had to buy an awful lot more kit. That was one of the reasons why it was economical for us to do. So it wasn't our problem, but it did mean new management systems and new management procedures. Fortunately, Verizon do use Nortel kit elsewhere in the network, so it wasn't too onerous, and that was all up and running by the end of December. Now, this is no experience without problems. You don't do anything without problems. And shortly after we brought the phase 1 stuff into service, we had a card failure, which is fairly regularly happens with the optical kits. It was backed off to their spares replacement, but there wasn't a card in stock, which was somewhat disappointing, or in the country, or anywhere in Europe. It had to be sourced from manufacturing, which fortunately only took about 2 weeks. That could have taken 2 months, really. But meanwhile, we had kept the 10 gig circuits around just in case something like this had happened, and there was still sufficient capacity, so it was just a matter of following it up contractually, whilst we then made sure, walked around their stocks and said, right, where are we going to have these cards? We want to see them. Again, like the trial, the logistical problems were much bigger than technical problems. All this involved weekly phone conferences for the best part of 6 months to get it working. And now the routers. So we started off with Juniper T640s at the points of presence. Now, for those of you that don't know, the T640 has got 8 chassis slots, 40 gig a slot. London and Reading would have 4 40 gig circuits, so half the chassis would just be for core links. So we decided to upgrade to T1600s. Now, the upgrade from a T640 to a T1600 is really pretty funky. It's completely in service. 1 power module at a time, you wire it up with an extra DC feed. You then change the fabric cards one at a time, and then put a new faceplate on so it says T1600 on the front. But the main issue for that was not service impact, it was getting persuading the telehousing providers that we could do it. Because the base power, well, the maximum power draw for the power rating for the T1600 is 9 kilowatts, compared to about 6.5 for the T640. And the Telehouse, Telecity were balking at that. And it took quite a while to persuade them that we aren't going to be running these things at the maximum power, that we really only be drawing maybe, well, we calculate, there are figures on the Juniper website, you can calculate what the routers are going to draw. And so we get, about close to 3 kilowatts than 9. Again, there were the odd problem. The first time the 40 gig links were brought up, the interface module on the Juniper needed to be bounced for the circuits to come up. It didn't happen again, even after circuit outages. And I was quite happy to leave it in that until Tuesday morning this week, when there was some reprovisioning work, and it did happen again, so we've got to follow that up. But otherwise, there isn't much to report. It did just work, which we'd been expecting, certainly for the IP kit. Whilst it's all quite new in the optical side of things, the Juniper interfaces for 40 gig had been around for a couple of years, and they should have just worked. So what do we have now? We still have the 10 gig a second links going up to Glasgow and Bristol, but now all the red links there are 40 gig. And do we need it? Well, the link from Telehouse to Telecity there is averaging, well, it's peaking about 15 gigaseconds. And traffic varies, someone mentioned earlier about the US inauguration. This was the Janet traffic on the day of, on January 20th. So we had our usual mid-afternoon peak. I mean, as you can see from our traffic, it's very heavily diurnal. It really drops right down during the night. Peaks about 2 p.m., but then we had another peak about 5 p.m. equal, so 35 gig a second coming in, and that graph on the bottom is one of the 40 gig links, so that was carrying 17.5 gig, close to that. So, well, should you go 40 gig, or if your network needs it? Well, that's not for me to say, but 40 gig has got very strict fiber requirements. The phase mode, polarization mode dispersion requirements don't fit in well with the old fiber that's in the ground in the UK. The aim for 100 gig by using the Polmux QPSK, and then by using coherent detection such as Polmux QPSK, will help things a lot further and bring the requirements for 100 gig down to much closer to the 10 gig fiber requirements. 40 gig is still expensive. There have been a couple of large deployments, mainly in the US last year, which might help, but probably not, because these are mainly line-side deployments, people multiplexing 1 gig, 2.5 gig, 10 gig circuits onto a single 40 gig wavelength. And it seems to be that SDH is reaching the end of its life. There's going to be no SDH standard for 100 gig or 120 or anything like that. Carrier Ethernet appears to be the way forward. And 100 gig standardization does march on. We started looking at it for technology trials. Again, like with the 40 gig, the line side stuff will be available before the client side. And we'll be doing trials soon, and we're thinking already about deployment in 2011, 2012. But will your chassis route or switch 100 gig a slot? And 40 gig does have the advantage that it is here now. A few quick thank yous. Verizon Business worked hard with us to make this happen, the optical equipment and the routing equipment, and that's me done. Any questions? Was that snow? Okay, well, thank you.